In this video, we're going to go over the dissolving process for ionic compounds. So when you have an ionic compound, you really have a crystal like this. So here we have a big crystal of ions. And so when we have the formula like this, NaCl solid, you don't really have just one sodium, one chlorine. You have a 1-to-1 ratio of sodium ions and chloride ions. So you can see here we have the purple is the Na plus, and then the green is the Cl minus. And so to dissolve it, you really have to separate those ions because you have an attraction between those ions. You have a solute particles attraction there, and we need to break those. And when you initially put that in water, you also have solvent-solvent attraction. So you have water attracted to water, and you need to separate them and then connect the water to the ions in the end. So before you dissolve, the bonds within the ionic crystal have to be broken. And then there has to be water ion attractions that are strong enough to break those ion interactions. So basically, it has to be worth it. Are the water ion attractions strong enough to break the ion attractions already there? If the ion attractions are much stronger than the water ion attractions, then the ionic compound will not dissolve. But if the water ion attractions are strong enough, then they can break the ion interactions and dissolving will happen. So the first main step you can see here is that as a water molecule approaches the crystal, they reorient themselves. The negative oxygen is attracted to the positive sodium, and the positive hydrogen is attracted to the chloride ions. And remember, the chloride ions are negative. Are negative. And so you can see that in this image here. This is really step one. You can see that the water molecules have oriented themselves towards the oppositely charged ion. So the hydrogens that are partial positive orient themselves towards the negative ion, the anion, and the oxygen that's partially negative orients itself towards the positive cation, the sodium. And our step two is that the water ion attraction is going to pull the ions away from the crystal. If that doesn't happen, if the solute attraction is way too strong, then it's going to remain undissolved. But otherwise, essentially what's happening is that the water is going to pull the ions away from the crystal. And that's really step two. And that has a term that is called dissociation. Dissociation. So that's when you separate the ions within an ionic compound. And that also includes bases. That's an ionic compound as well. Dissociation really happens for ionic compounds and bases. It doesn't happen for molecular compounds. Okay, it's really just for ionic compounds. We'll see what happens in molecular later. So we can actually write an equation to represent the separation of the ions when something is dissolving. And so let's say we want to dissolve some NaCl solid. We'd put NaCl, and we'd put solid first, and we put an arrow. And now I want to emphasize this is not a chemical reaction. It's still a physical reaction because you still have Na and Cl. They're just separated and surrounded by water at this point. But you're going to write Na plus, that's the charge for sodium, plus 1. You're going to put Aq because it's dissolved in water, plus Cl minus, and you're going to put Aq because it's dissolved in water. These charges come from their periodic table, and I'll put -1 just to be more clear. And aqueous means they're dissolved in water. Again, this is not a chemical reaction because it's dissolving, and dissolving did not change the fact that it's NaCl. It's just that they're separated now by from each other because water kind of came in between them. So this is not an example of decomposition. Remember, decomposition was a chemical reaction where you had sodium atoms produced and chlorine gas produced. These are not the ions anymore. So because these are not the ions, these are totally different compounds altogether. So this is a physical process of dissociation. It's a physical process. We'll try a few more practice problems together. So let's say we want to dissolve sodium carbonate. This is an ionic compound. I know that because there's a metal there. And I want to write down how it will dissociate in water. So what I can do is I can write first the sodium ion is 2Na, or is Na plus, aqueous, and it's +1 because it's in group 1. And then the charge of the carbonate is simply CO3, 2 minus aqueous. And that's because that comes from our polyatomic ion table. And you can balance this as well. Notice there's 2 sodium, so you can just put 2 like that. But the main point is that you've shown this dissolved. It started off as a solid, and now they're both aqueous because they're surrounded by water particles, or they're about to be surrounded by water particles. So really, this equation, what you've drawn out here, this NaAQ and this Cl minus AQ, this is really NaClAQ. So when we say NaClAQ, that really means you have sodium ions and Cl minus ions separated by water. Same idea here. When we say you have Na2CO3AQ, that means you have sodium ions and carbonate ions separated by water. And you can probably guess that the water, for example, for the Na and the CO3 minus here, the water, the hydrogens would surround the carbonate, and the oxygens would surround the sodium, because partial positive is attracted to negative, and partial negative is attracted to positive. You can try the next one on your own. Try to write a dissociation equation. Remember, dissociation equations always start off with the solid substance, and then you separate it into its ions. It's not a decomposition, it's a dissociation, because you still have that compound just separated by water particles. So potassium is K plus 1, and that's AQ. And then phosphate is PO4 3 minus. That's from the polyatomic ion table, and that's AQ as well. And if you want to balance, you have 3 potassiums there, so that's 3 like that. And that's a dissociation equation for the potassium phosphate compound being dissolved. And so essentially what happens is dissociation happens, so your ions are separated, and water surrounds your ions. So we have a bunch of water particles surrounding the chloride ion over here, and a bunch of water particles surrounding the sodium ion over here. And that process of the water particles surrounding your ion, that's called hydration. Hydration. In fact, the actual water that surrounds it is called a hydration sphere or hydration shell. Okay, so again, the water orients itself to face its proper ion based on the atom. So hydrogen faces negative ions, oxygen faces positive ions. The water will basically drag away the ions bit by bit from the larger crystal, and then the water will surround the ion, each ion. So we'll have water surround the negative one, and water surround the positive one, and that's called a hydration shell, and that process is called hydration. So what I want you to know about ionic compounds is that, as you can see, when they've dissolved, they've actually formed ions in the solution. They have some Na plus and Cl minus in there, so there's charges swimming around in the solution. So that's the reason why when you dissolve an ionic compound, you're actually able to, it actually conducts electricity. So ionic compounds dissolved in water can conduct electricity. Ionic compounds, and here's the interesting part. So let's take a look at this figure over here. We put a light bulb in here to test conductivity of different things. We put this into pure water where there's no ions, and notice the light bulb does not glow. Then we put this into sodium chloride. This is solid sodium chloride here, solid, not dissolved in anything. And notice that the light bulb did not glow. But as soon as we put it in dissolved sodium chloride, NaClAQ, the light bulb does glow, because now those sodium and chlorine ions are free to move around, chloride ions are free to move around within the water, and so they can conduct electricity. Whereas here in the solid, the solute particles, the ions, are just so attracted to each other that they don't really move, and they're very rigid, and they can't conduct electricity. And so that is the reason why ionic compounds dissolved in water can conduct electricity. So what we've seen is the dissolving process for ionic compounds. We've seen how to write dissociation equations as well. The process involves essentially separating the ions from the larger crystal, and then water particles surrounding the ions. You should be able to write dissociation equations, and you should be able to demonstrate the dissolving of an ionic compound using a diagram like this. So could you show, how many, could you show water particles surrounding the proper ions and in the proper orientation? Could you show how the water would approach the crystal, for example? Could you show partial charges on your water as well? In the next video, we're going to take a look at how molecular compounds dissolve and how that's different from the process of ionic compounds dissolving.